Hello, can you hear me? Okay, thank you. Yeah, so hi, my name is Rohit Kumar Singh, teaching assistant for this course, Wave Optics, and this is the 7th live session. So instead of Saturday, we are doing this today on Friday because I'm traveling tomorrow, so that's why I shifted it. So, yeah, in the last session, we looked at diffraction, basically Fraunhofer diffraction, and we solved some examples. And so uh, today also we will have review some topics from diffraction, like n slits, what happens when you have n number of slits, and the concept of diffraction grating and resolution power of diffraction grating and things like that, and we'll solve some problems based on them. Okay. uh, so yeah, let's start. So last week we looked at the two slits, diffraction due to two slits. Okay, two slits Fraunhofer diffraction. And so if you remember, what we did was, suppose these are the two slits and they are separated by a distance d, and the width of each slit is b. Okay, and what we did was we divided the each slits into different zones. Okay, like A1 and A2. Okay, and then we looked at uh, I mean so suppose, yeah, from A1 there is a light ray going like this, A2 going like this, and so on. And this is a point where we are looking at the screen. Similarly, for this the other slit also, we will have different points. Let's call them B1, B2, so on. And we calculated the electric field, resultant electric field at P due to these two slits. Okay, and the formula looked like so. It was just the sum of the two individual electric field, and we got something like this. So sine beta by beta, and we had this sorry, there was a cos gamma term. So I'm just recapping it because I'll discuss the n slits today, so that's why just quickly recapping this. Okay. By the way, did we discuss n slits in the last session?
No, sir.
Okay, then fine. Okay. Yeah. So this was the resultant electric field due to two slits. Okay, and where gamma was just phi 1 by 2. Phi 1 is the phase difference, which was 2 pi by lambda d sine theta. So 2 here, so it is just pi by lambda d sine theta gamma. And yeah, so this was, and the resultant intensity was just square of this amplitude, which was 4 I naught, sine square beta by beta square cos square gamma. And we can recognize this one as the diffraction due to single slits. So single slit term, and this is due to the interference from the two slits. Okay, so this was this we did. Now yeah, and the condition for maxima was this. So yeah, so the condition for interference maxima was d sine theta is equal to n lambda, right, where n could be 0, 1, 2 and so on. And we know that the condition for diffraction minima is given by b sine theta by m lambda, right, where m is 1, 2, 3 and so on. Now here one interesting thing happens, like that we discussed also last time, that when these two equations are simultaneously satisfied, then there will be missing interference maximas. Okay, for example, so this is your intensity, so you will have a maxima like this, then okay, and then you will have another maxima and so on. Now so suppose this is your third order maxima, third order interference maxima, right, and simultaneously if this equation is also satisfied for m equal to 3, then this will be missing in your spectrum. Okay, you will not observe this one. So based on this, there was one problem that we got confused. So first let me write what do we mean that this equation is simultaneously satisfied. It simply means that if you divide these two equations, you can get this formula, right? So just divide this and rearrange a little bit. Okay, then maxima will be absent. Okay, m order maxima will be absent, which we called missing orders. Now this means that for any integer, okay, integer value of n, okay, that results in an integer value of m, then mth order maxima will be missing. So what does that mean? Okay, so let's that will be clear. Let's solve the problem that we got confused last time. Okay, so this was the problem. Okay, so what does it say is a double slit diffraction pattern is formed when using mercury green light 546.1 nanometer. So lambda was given 546.1 nanometer, and slit width is given. Each slit has a width of 0.1 millimeter, so b is given. Okay, and also it's given that the fourth order interference maxima is missing, that is m equal to 4 is given. Okay, and the question asks the slit separation, that is d. Okay, so this was the problem. Now to solve this, just simply write this equation. Okay, so m equal to d by b times n. Fine. Now m is given, which is 4. D we have to find out. B is given, which is 0.1, and n we have to calculate. So now what did I say? So for any integer value of n, that results in an integer value of m. Okay. Now tell me, for which value of n that so m is given here, right? 4. Now what values n can take? So n can be 1, 2, 3 and so on, right? Now if n equal to 1 is there, yeah, if n equal to 1, let's put n equal to 1, what do you get? D equal to, or let's write this equation. So d by 0.1 into 1. Okay. This equation satisfied, right?
Yes, sir.
Yeah, but let's see for n equal to 2. Okay, now what happens is yeah, no, okay, wait, no, we cannot region like this. Again I'm confusing, sorry. Let's not like this. Okay, so this is the criteria, this is the equation. Okay, now to solve this kind of problem, you have to go back to the options. Okay, so if you put d equal to 0.2 here, so first option, so this is this cannot be satisfied for any value of n, correct? Because the minimum n can take is 1, right? And for n equal to 1, on the left hand side you have 4 and on the right hand side you will get 2. So that means d cannot be equal to 0.2. Is this fine?
Yes, sir.
Yeah. And then what the next option, which is 0.4. So if you put 0.4 here, then this is satisfied with n equal to 1, right? Because you get 4 here and 4 here. Okay. Similarly, you can check for the third option also, like 0.6. For 0.6, n equal to 1 will not satisfy. I mean, no matter what you take this equation, I mean left hand side, you cannot get the left hand side or right hand side equal to 4, right? Because it is already 6, and whatever you multiply it with, it won't go back to 4, correct? So that's why the only option that is correct is B, 0.4 mm. For all the other values, you cannot match the right hand side and left hand side for any value of n. But if,
sir,
yeah,
for the first option, and we can put n is equal to 2. For that it satisfies, right?
yeah, but you have to check the minimum, yeah, you're right, but you have to check the for lowest order of n, that this equation, because see, the fourth order is missing, right? Fourth order is missing means so first 3 orders are there, okay, and the fourth order is missing. That means you have to check the minimum order of the diffraction minima, that is that can satisfy this equation logically.
Yeah, okay. Okay, sir.
Okay. So this is this is how you'll have to solve this. So okay, let's solve one another problem based on this, then it will be more clear. So no, this is a another one, which is Fraunhofer diffraction pattern is observed by a double slit having a slit width of 0.16 mm. So let's represent it by B. Okay, B is given, and the separation between the slits is given, which we are calling D. So let's call it by that. Now we have to find the missing orders. Okay.
Sir, I
Yeah.
have a doubt.
Okay.
The way we told minimum we have to calculate n should be minimum.
Mm-hmm.
But n means they have not mentioned it, right? And n is equal to 2, that can also be correct here.
Yeah. But no, they have not mentioned, but they have written that the fourth order interference maxima is, so fourth order m equal to 4 is missing. Okay. Now that means that m equal to 4 overlaps with the first order of the minima, diffraction minima. Okay, that is, I think, explicit. If it is not given, you have to assume it. Otherwise, yeah, you are right. The then n equal to 2 is also can be true here, and then you have this discrepancy that 0.2 mm will also be the correct option. Correct?
Yes, sir.
So see, what I just mentioned is that, so this so in this diffraction pattern, if any interference maxima is missing, that means so if the third order is missing or fourth order is missing, and similarly if nth order is missing, if the problem says so, okay, that means it is so there is second order also, right? So if second order and third order are both missing, then you can say that, okay, second order might coincide with the first order of the diffraction minima, and this third order coinciding with the second order of the diffraction minima, or whatever the next order is. But if only one order is missing, that means that is coinciding with the minimum order of the diffraction minima. Okay.
Yeah, okay. Means they are telling about the very first which is missing.
Yeah, because the first interference maxima is missing, that means that is coinciding with the first diffraction minima, right?
Yeah, okay, I understand now.
Yeah.
This is an assumption, we have to take this in mind.
Yeah,
before
I mean,
solving,
yeah,
right?
otherwise, yeah, there is this discrepancy will come. That's why we got confused last time, because both options were looking correct. But you have to assume that the first order minima is coinciding with whatever interference maxima is missing. Then if the problem will say, okay, sixth order interference maxima is also missing, then you will say, okay, then the n equal to 2 might coincide with the interference maxima of sixth order. Okay.
Okay.
So-
Language of the problem, then,
Yeah.
you can say.
So like in this problem, let's see. Okay, so only B and D is given. Okay, and we have to find the missing orders. Okay, so what is our criteria? M equal to D by B n, right? Now you see, D by B is what? So 0.8 divided by 0.16, so it will be 5. So m equal to 5n. So this is now our condition. Now for n equal to 1, 2, 3, 4, 5 and so on, what will be m? 5, 10, 15, 20 and so on, right? So you see, the fifth order interference maxima coinciding with the first order minima, 10th order coinciding with the second order diffraction minima and so on. Understand? So these will be your missing orders. So the missing orders always comes in sets. Okay. So if this kind of problem comes where you have to find the slit separation and it is not given which order of diffraction minima is coinciding with the interference maxima, you have to always assume n equal to 1 minimum. Okay, that will work. If it is not given in the problem, if it is given, if the problem would have said that okay, fourth order is coinciding with the second order of interference diffraction minima, then we will have to take n equal to 2 and the answer would be 0.2 mm, but that is not given, so we have to assume n equal to 1. Okay, so just keep that in mind. So okay, so this was a topic from last lecture. So now let's look at if you have, instead of 2, if you have n number of slits. Okay, so then what happens? So instead of 2 you have n number. N can be anything from 3 to 3000, doesn't matter. So yeah, this goes on, and there is your screen. So we will assume the separation, I mean the adjacent separation is D between the slits as always, and each slit width is again B, so everything is same. So just a generalization of this one, instead of 2 you have n number of slits. Okay, and everything is same. Now in this case, like we did here, if you remember, we calculated E1 and E2 and then add them up and we got this. So likewise here also you can calculate E equal to E1 plus E2 plus whatever En that you have, and this will be equal to something like so I am writing the resultant one. I am not going into the derivation. I'll just say few things about the difference between 2 slits and n slits, intuitively what is happening. Okay, now you see these two formula, we had this and now we have this. Okay, now you see, instead of cos gamma we have sin n gamma by sin gamma, right? And instead of half phi 1 here, yeah, you have now, so half, instead of half phi 1 you now have half n minus 1 phi 1, which is so this is basically total phase shift that you will get from here to nth slit. Okay, and divided by 2 obviously, and this you see, if yeah yeah, so this is and this is the another substitution when you go from 2 to n slit. Now you will see very interesting thing, and as usual gamma is pi by lambda d sin theta, that is the same, which is also equal to phi by 2, and the intensity now is given by I naught sin square beta by beta and sin square n gamma by sin square gamma. As usual, this is the single slit diffraction intensity, and this is the interference. This is the intensity coming from the interference of all the slits. Okay. Yeah. Now where you will have maxima, I mean the interference maxima. So as you can see, interference maxima should be at equal to like m pi, gamma equal to m pi. I mean it is not straightforward, but you can derive this. So if you just put, so basically at gamma equal to m pi, I will be equal to I naught sine square beta by beta times n square. How did I write this? So you can take this interference term, now if you put naively m pi in this equation, gamma equal to m pi, what will you get? You get 0 by 0, right? This is just 0 by 0.
Yes, sir.
So you have to use, limits. So this is what we call in what do you call in limit and continuity, some indefinite form or something, right? So then you have to use limit to get a finite value out of this. So if you let gamma tends to m pi, then this L'Hospital rule that you can differentiate numerator and denominator, right?
Yes, sir.
Yeah. So I mean let's do it for simply n not squaring up. We'll square later. It doesn't matter. Just makes the differentiation simple. So differentiating the numerator, you will get n cos n gamma, and here you will get cos gamma. Okay. And now if you put gamma equal to m pi, so this will be 1 and the denominator will also be 1, so you will get n. So hence I has this n square term. Okay. So sine square n gamma by sine square gamma tends to n square. Is this okay? So the interference pattern will look something like this. So as function of gamma, if you plot this sine square n gamma by sine square gamma, so at m pi means 0, pi, 2 pi, and similarly minus pi, minus 2 pi, the interference I mean this value is simply what? N square, right? Sorry. This is n square. So you have this, and then there will be secondary maxima here. Then again you have this, and so on. All of them, all of these heights will be same. So on. Okay. So it will look something like this, the interference, the intensity due to the interference of n slits. And you see that it all depends on how many number of slits you have. If you have more number of slits, then the these maxima. These are called principal maximas. Okay. So you will see more bright intensity. The more number of slit, more number of bright intensity you have. Okay. And then what about minima? What these minima will correspond to? So I equal to 0 will be always when we know that this is from the single slit. This will always be there, right? B sin theta equal to n lambda, n equal to 1, 2, 3, because this is the diffraction term from a single slit, right? So this will be there, or either n gamma is equal to some p pi, where p should not be equal to n, 2n and so on, because at n, 2n and so on you get gamma equal to pi 2 pi, which is principal maxima, right? So this should not be there. Is this fine? So these two are the condition for minima. Okay. Now we can put the value of gamma here in this equation, and then you can get this criteria of d sin theta equal to lambda by n, 2 lambda by n, and so on. So let me write this explicitly, because there is something interesting here. Okay. So this we said that p cannot be equal to n, 2n, I mean the like integer multiple of n. Okay. So that means, okay, first will be lambda by n, then 2 lambda by n, and then so on and on. We will have one n minus 1 by n into lambda, but then we will not have n by n lambda, right? This cannot be there, because this is the condition for principal maxima, right? So then we have to jump to n plus 1 by n lambda, and then again we have n plus 2 lambda by n, and so on, and then again we will have 2n minus 1 by n lambda, and then again we will not have 2n by n, right? Because this is just 2 lambda, which is the condition for principal maxima. So this we will not have. The next one will be 2n plus 1 by n lambda, and then so this list goes on. So you can see here there are n minus 1 minima. So these minima that are there between two maxima. So n minus 1 minima between two principal maxima. Do you understand, or you got confused? Let me know if I can explain again. Fine for everyone? This is very important to understand, because yeah, we saw that, okay, gamma equal to m pi was our principal maxima, okay, and then gamma equal to m pi will be gamma equal to m pi, or n gamma equal to m pi p pi, which will also be the condition for minima, right? But whenever p equal to integer times n, then you will get the condition for maxima. So other than those, whatever values you will have for gamma, those will correspond to minima, and so these are the values for minima. And as we seen there, as we have seen there, so this is one set of minimas. Okay, then here you will have a maxima, then this is another set, this is another set, sorry, this is another set of minimas, then here you will have a maxima, then this is another set, and then it will go on and on. Okay, which corresponds to these minimas. Then you have principal maxima, then minima, I mean number of n minus 1 minima in between, and then principal maxima, and so on. Okay. So that's how you have to understand it. Is this fine? Okay, thank you. Now here also, like in the double slit thing, in double slit case, a particular principal maxima can be absent. Okay, a particular may be absent. So when that will happen, when if your so this is the condition for interference maxima, m pi, right? And you always have this condition for diffraction minima, right? N lambda, where n equal to 1, 2, 3, so on. So if these two equations are satisfied simultaneously, then your m order of interference maxima will be missing. So and I mean the criteria is same, like this condition will hold here also. Okay, same condition. So if you look at a pattern of n slits, diffraction pattern, you will see some principal maxima are absent, and that those correspond to these diffraction minimas. Okay. So same concept applies here also from two slits. Now, what about this? What about this width of this angular? I mean, this principal maxima. If you want to calculate the width, the angular width of this principal maxima, like we calculated fringe width in case of two slits, Young's double slit experiment. So likewise, we can calculate the angular width of this principal maxima, and to do that, so width of this principal maxima. Okay, so let me again write the criteria for principal maxima, which is d sine theta. So for order m, I'm writing theta m. This theta is different for different order of principal maxima, right? So m equal to 1, 2, 3, and so on. Okay, this is the criteria. Now you can see here, so let me draw one of the principal maxima. So let us have this principal maxima. Okay, and then you have these minimas, the n minus 1 minima around each principal maxima. Okay, and this is your theta m. Okay, so there will be two minima, one is here, one is here on either side. Okay, and let's call this angular width delta theta m. Okay, so two minima on either side with angle theta plus delta theta m and theta m minus delta theta m. Okay, so this angle will be theta m plus delta theta m, and this angle will be theta m minus delta theta m. Fine. Now yeah, now what condition do we have for the minima? D sine theta, d sine theta m, sorry, m is the maxima. Okay, in general d sine theta m should be equal to what? In general, can we write it like this? Can you understand it? In general, this equation can be written like this. Are you okay with it? Because you can put m equal to 0, then you will get these sets, right? Then you will put m equal to 1, you will get this set, and so on. So this is, this long equation can be written in concise way like this. So basically m corresponds to all these principal maximas, and then you have n minus 1 minimas in between them. Okay, so that is the criteria basically for minimas. Is this fine? Okay, great. Now what is the angle for these minimas? So theta is basically here theta m plus minus delta theta m, right? This is the angle, so let's put here. So please let me know if you don't understand anything, I can explain again, okay? Fine. So this is the minima condition. Now we can use the formula for sine a plus b to expand it. So you will get d sine theta m cos delta theta m plus minus cos theta m sine delta theta m is equal to m lambda plus minus lambda by n. Now assuming this delta theta m very small as compared to theta m, so this can be approximated as this. Is this fine? So what we have done is we have used this approximation, and cos delta theta m is equal to 1. Okay, because delta theta m is smaller than theta m. And here you have m lambda plus minus lambda by n. Now you see this is equal to this, right? So it cancels out. and what you are left with is delta theta m is equal to lambda by nd cos theta m. So this is the angular width of the these principal maximas, right? This width you have calculated basically. 2 times of this will be the total width of this maximum. Is this fine? You understood all the steps?
Yes, sir.
Okay, thank you. Now, one interesting thing to see here is that this angular separation or angular width of the principal maxima, it is inversely proportional to n. That means if you increase the number of slits, this decreases. Okay, so your principal maxima gets sharper, right? Becomes sharper as n increases. So this is one thing you can deduce from here. So which makes sense because we know that with n increasing n, the intensity also increases by n square. So that's why this they become more sharper, which we also derived here. Okay. Okay, fine. Now then, let's quickly discuss this diffraction grating. Then we solve some problem. So diffraction grating is nothing but this n slits, but they are just. I mean, in practice, we use this diffraction grating in labs to study this Fraunhofer diffraction by n slit. So what is the diffraction grating? So basically you take any transparent material like scale kind of material, and you print on it, or basically draw lines on it using something called grooves. They have diamond needles. You put lines, equally spaced line like this, and you get diffraction grating. Okay, so these are basically n slits that you draw on it, and everything is same for this. So you have this condition for principal maxima. So this is nothing different, it's the same thing. And here this is called grating equation. Okay. Now one thing to notice here is that you can take a diffraction grating, put a white light, like shine a white light on it, and you will observe spectrum, like it will act as a prism. Okay, so you will get all the wavelength of the light distributed, like you will see red, yellow, green, everything. Now how does that happen? So as you can see here, so for m equal to 0, what happens? Theta m is basically 0. Like you have this maxima, right? Central maxima, right? So that will be white. But for m not equal to 0, theta will be different for different lambda, right? For different wavelength. So if you shine a white light, because white light has this all of the wavelength of the spectrum, and all of them will have a different theta. So your white light will be separated in all the different wavelengths that constitutes the white light. Okay, so it will act as a prism. And if you differentiate this equation, you will get this. This is called angular dispersion. Okay, so this is basically how much angular separation is there for change in wavelength. Okay, so we will solve some problem, and that will become clear what I mean by the angular dispersion. Okay, so yeah, just keep this formula in mind. So this is called angular dispersion. Yeah, or relative angular dispersion, because it is with respect to the change in wavelength. Now there is one more concept, which is the resolving power of a grating. So as I mentioned, if you're using white light, which has all the different color of wavelength, so and you can separate all those wavelengths. Okay, so basically you are resolving different spectral lines, right? Now similarly, if you have very that the sodium lamps like basically emit two different wavelength of light very closely spaced, and if you want to look at them separately, you can use a grating to resolve those two wavelengths. Okay, and the resolving power is given by this formula, lambda by delta lambda. So this is basically for if one of the light has wavelength lambda and other has lambda plus some like delta lambda, little bit greater than lambda, then this is the resolving power of the diffraction grating. Now this doesn't like tell you many things. So what does that mean? Like this resolving power, how it depends on the number of slits in the diffraction grating, for example. So to look at that, there is something called Rayleigh criterion. Now what Rayleigh criterion means is that, so you have, suppose for a given wavelength d sine theta equal to m lambda, this is the condition for principal maxima, right? So you have this principal maxima, okay, and then you have another one, and this is the minima. So this is for a given wavelength. Now if you have another wavelength of light which is lambda plus d lambda, right, and the principal maxima for this will be little bit shifted. For example, so I am drawing this like this, okay. So suppose this is for lambda plus d lambda. Now what Rayleigh criterion says is that if the principal maxima of lambda if the principal maxima of lambda plus delta lambda falls on the first minima of the principal maxima of due to the lambda, then they are said to be just resolved, then we can say that these two wavelengths have been resolved. You can clearly distinguish them. So this is what resolving powers mean. Resolving power mean. So let me write it. So if principal maxima corresponding to lambda plus delta lambda falls on the first minima of lambda. So this is the first minima. It is falling on the like this principal maxima is coinciding with the first minima of lambda. Then the two wavelengths lambda and lambda plus delta lambda are said to be resolved. Okay. So this is the, as I wrote, this is the condition. This is the principal maxima for delta plus lambda plus delta lambda, and you can, and this is the condition for minima, first minima of lambda, right? So these should be simultaneously satisfied. So if you like equate these two, you will see that these cancels, and R equal to lambda by delta lambda is nothing but m times n. Okay. So here also you see the resolving power is directly proportional to number of slits. Okay. Obviously also on the order of the principal maxima. So more the number of, like higher the number of the principal maxima order, the more resolution will be there. Okay. Is this fine, or any dot is there? Did you understand what I mean by resolution? So that you can look at the diffraction pattern, and you can say, okay, these two wavelengths, the principal maxima corresponding to these wavelengths are separated from each other, like resolved. That is what resolving power means. Like you can tell clearly that there are two separate wavelengths. Okay. Because if it comes more closer, then they will get merged and you cannot tell them apart. So this is the minimum criteria you need to have, like the maxima should fall on the minima of the other one, so that you can tell them apart. So this is the concept. Is this fine? Great. Okay, let's solve some problems, and then things will be more clear. So this we solve, this we solve. Okay, there is one problem on the grating, diffraction grating. So how many orders will be visible if the wavelength of the visible light is 560 nanometer and the number of lines in the grating is 440 per mm. Okay, so you have 440 lines per millimeter, and the wavelength of the light is given, which is 568 nanometer. How do you calculate the orders that will be visible in the diffraction pattern?
Sir, I have a doubt.
Yeah.
You said the two maxima to be resolved,
Mm-hmm.
minimum should be there, means like the maxima should fall on minima,
Yeah, yeah.
principal maxima. But why, mean if they are not that much separated,
Mm-hmm.
if they are closer than that,
Yeah,
you
yeah,
said resolution won't be there. Why?
yeah, yeah, yeah. So, I mean, okay. So suppose you are looking at some thing. Okay. Suppose you are looking at two spots of light. You can tell them apart. Okay, right? Now, if I move it closer, now they look like, still they look like they are apart, like there are two spots, right?
Yes.
But beyond this you will see one single blob, right? So this is what happens. So when you look at the diffraction pattern from above, okay, if these two are coming more closer together, so this is the criteria. So here what is happening is the maxima of one is falling on the minima of the other. More closer than this, it is very difficult to tell them apart. Okay.
Is it experimental observation?
I mean, it is
Or
one
any
standard, standard criteria. So I mean, if you have very sharp eyes or your instrument is very fine, you can still like see and tell them apart. But this is a standard definition of resolution. That is what we mean by resolution. Okay, yeah. Obviously, it varies from experiment to experiment, right? But this is
okay.
a criteria given by Rayleigh that okay, so we will call it resolved. Like we are 100% sure that these two are different spots if this criteria is satisfied. Okay. So it's a standard thing. And this is this is very general thing, you will find it everywhere. So uh, if you are looking using a telescope to look at stars, if the two stars are very close together, uh, how will you say that they are two different stars? So you have to use this Rayleigh criterion there also. Okay. So these things are or using a microscope you are looking at anything, also you can use the resolution power. I mean, you can calculate the resolution power by the same concept. So yeah, it is a very general thing in optics. Okay, yeah. Is that fine?
Yes, sir.
Okay. So okay, coming to this problem now. So do you understand this one? So it's saying how many orders would be visible. So orders means m. Okay. So why does it say how many orders? Can't we see all the orders with a diffraction grating? Why there is a problem that we can see only few orders? Any idea? Because you see, we have the grating equation, this, right? And the maximum possible order, so m max, maximum m will occur when sine theta equal to 1. So there is a limit to sine theta, right? Or
Yes.
m max is equal to d by lambda, right?
Yes, sir.
So lambda is given, d we have to find out. So for d, so d is what? D is the slit width, basically distance between the two slits. But that is not given. What is given is that there are 440 slits per millimeter. So what is the separation of a single slit? So that means okay. So n will be what? 440 lines are there per mm. Okay, that means 440 into 10 to the power 3 lines per meter. Okay, and distance of one, like width of one line would be what? 1 over n. Correct? In meters, this will be around 2.27 into 10 to the power minus 6 meter. Do you understand this? So you have 4 foot, I mean this much lines in a meter. Okay, so you have 440 into 10 to the power 3 lines in 1 meter of distance. So then you have one line in 1 by 440 into 10 to the power 3 meter, right? And this one line correspond to one slit. Is this fine? Yeah, so just we'll put this value here, and lambda is given 568 nanometer, so 10 to the minus 9. So this is 10 to the power 6, so it will be around 4 times, I guess. You can check. So only 4 orders will be visible. Okay, 440 lines if you have, only 4 orders will be visible. So if you want to see more orders of pattern, like interference maxima, then you have to use more number of lines in a meter. You have to increase to 1000 or 10,000, whatever. More lines will be there, the more orders will be visible. Is it fine? Okay. Now let's go to the next problem. Yeah, this is we just discussed this. What is the angular separation between the second order principal maximum and the neighboring minimum on the either side of a Fraunhofer pattern of a 24 groove grating having a groove separation of 10 to the power minus 3 centimeter and illuminated by a light of 600 nanometer. Okay, so what it is asking us, the angular separation between principal maximum and neighboring minimum. So basically this separation, this delta theta that we calculated here, right? Yeah, where did we calculate it? Yeah, this we calculated here, which is lambda by nd cos theta, correct? Yeah, cos theta m. And in the problem, lambda is given 600 nanometer. So this for 24 groove grating, I told you that we need grooves, like we use grooves. So 24 means basically n equal to 24, like there are 24 number of slits basically. Okay, and what else do you need? D is so and they are separated by 10 to the power minus 3 centimeters, so this is your D. So yeah, but we need the cos theta also. So how can we calculate the cos theta? Any idea? we have the grating equation, right? And it is given here that second order principal maxima. So m is equal to 2, lambda you know, d you know. So we can calculate sine theta, right? 2 lambda by d, and from sine theta you can calculate cos theta, right? So this will be 2 into 10 to the power 2 into 6.0 10 to the power minus 7, because it is in nanometer, and d is 10 to the minus 3 centimeters, so 10 to the power minus 5 meter will be 0.12, and corresponding to this you have cos theta equal to around 0.99. Okay, so did you understand how I calculated cos theta? We use the grating equation. Okay, order of the principal maxima was given, so this way we calculated it. Is this fine? And then you can calculate the delta theta by putting everything. So it will be 6 into 10 to the power minus 7, 24 into 10 to the power minus 5 meters, 0.99 for the cos theta. You will get around 0.144. So as you can see, this is a very small angle, right, which is expected. Okay, is this okay? We can go to the next problem.
Yes, sir.
Okay, thank you. Yeah. Another simple problem based on the formula. So light of wavelength 500 nanometer, 500 nanometer, incident normally on a grating with 5000 grooves per centimeter. Okay, so 5000 grooves per centimeter given, and we have to determine its angular dispersion in the first order. Okay, so 4m equal to 1. So we have the formula for angular dispersion, this one, delta theta by delta lambda is equal to m by d cos theta. Okay, and so yeah, we have everything. M is given. So what about d? So d will be 1 over 5000, right? Not 1 over 10 to the power minus 3, because it is 10 to the minus 2, because it is given in centimeter, we have to convert it into meters. So this will be the separation, slit separation, right? And again cos theta we can determine using this grating equation. So from here, so cos theta will be 2 lambda by d. So yeah, if you put it here, oh sorry, no, this is sine theta, sorry. Yeah, this is sine theta. So again, like here we can calculate cos theta and put it here, and you will get that. Should I solve it, or is it okay to leave it?
It's okay, sir.
Okay, so the option is this one. Okay, you can solve it and get the answer. So yeah, I mean, you have to just find out what is given in the problem and use the formula that is appropriate for it. Okay, So there just few formulas are there. Okay, then let's move to the next problem. This one is the last. So yeah, okay, so we have to calculate the least width that a grating must have to resolve two components of sodium D lines in the second order. Number of lines per mm is given 80. Okay, so this one is again problem on the resolving power of the grating. Okay, so what was the resolving power? Lambda by d lambda, which was equal to m times n, right? So yeah, how to solve it? Any idea? So you have to find d, but that is not there in the formula. How do you find it?
D sin theta is equals to m lambda plus lambda by n.
Yeah. So yeah, you're right. D sine theta is equal to yeah, m lambda plus lambda by n. Okay.
Yeah, one more equation was there. D sin theta equals to lambda plus delta lambda.
Yeah, and I mean from there we find we have this equation, right?
Yes, sir.
So from here what you can calculate is, so you have given lambda, and delta lambda you can calculate. So delta lambda is just 589 point, I mean just subtract, you will have 0.6 nanometer, correct? And yeah, yeah, this equation will not help here, right? You're right. And then you have another equation which is oh yeah, so m is given second order. So if you put here 2 lambda by n, okay, and then for the lambda plus delta lambda, which is basically this wavelength, you should have the condition of maxima, which is what? Which is just 2 lambda. So this is so lambda plus delta lambda, right? Now how do you solve this equation to find d? Because if you subtract them they get cancelled, right? It is not that simple. Wait, number of lines per mm is given. Okay, so I see. Okay, number of lines per mm of the grating is 80, so that means 80 lines per mm is there. Okay, so for one line you have 1 by 80 or 10 to the power minus 3 by 80. This is the this should be the slit width, no? Why?
Yes, I thought it's in beginning.
Ah. Wait, no, there is a trick. Least width that a grating must have. So, okay, I think from this equation we can find out simply the number of slits. Okay, is that fine? So n is equal to this, right? Lambda we have 589, m we have 2 into 0.6 delta lambda. So if you calculate this, it will be around 491. So since it should be an integer, so you have to take 491. So this much is the number of slits. Okay, and from here we find that there should be the width of each line is this. Okay, 10 to the power minus 3 by 80. Okay, number of lines per mm. But we find out total number of lines. Total number of lines is this. This question is confusing. Okay, 491 by 80. If we do, what should be the answer? Should it comes close to 6.15, right? So somehow this question wants us to divide this by 80, which makes sense if there are total number of 491 lines and number of lines per mm is 80, then yeah, one line, this is the width, 491 lines, 491 divided by 80, this is the width. Sorry. Okay. Yeah, I can. I don't understand why.
Are they talking about the dimension of grating itself?
Wait. Calculate the least width that a grating must have. No. Are you? Oh yeah. You're right. Sorry, yeah. I think it's talking about the width of the total. Whole grating, right? Yes, you are right. It is talking about the whole grating, not the width of one single slit. Sorry. Yeah, I misunderstood. Yeah, you are right. Yeah. Then it's fine, no? Yeah. Sorry. Yeah. Okay. See, you guys are better than me. Very good. So yeah, then it makes sense. So your grating must have width of 6.15 millimeter, and then the number of lines per millimeter of that grating should be 80. Then you will be able to resolve these two sodium lines. Great. Okay. Nice. So everyone understood this problem? I got confused. I thought it's asking the width of one slit, but it's asking the width of the total whole grating. Okay. Is anyone has any doubt? Okay, then if no, then yeah, this was the last problem. So that's it for today. Thank you for joining. Uh, that so the next session will be on next Monday. Okay, like not the coming Monday, the Monday on the next to next week. So you will get the notification because I'm again traveling on next Saturday. So that Saturday session I'll conduct on Monday. So I hope you will join. And sorry for you for any inconvenience. Uh, yeah. Okay.
Sir, Monday on what time?
Monday this same time 3 to 5.
Okay, we have classes
Yeah, I
generally on.
understand. Yeah, I understand. If you have class
Can we shoot 4 or 5 p.m. starting time?
5, we can do it from 5. Okay, then I'll tell them to give the notification for 5 to 7. Okay.
Yeah, okay, sir.
Okay, thank you. Okay. 6. Yeah, 6 also we can do. Okay, 6 to 8 then. Yeah, fine for me. Okay then. Okay. So yeah, then let's see you. See you Monday. Okay.
Sir, what
Yeah.
about you said about one extra class?
Yeah. Extra class that will be after the 12 live session, like in the end.
Yeah, okay.
Okay. So yeah, there we'll discuss the favorite period. If you want, we can discuss it in one of the lectures. If you want, I can discuss it. Do you want to discuss it now, or you want to leave it as a special topic for later?
Today?
No, not today. Like in the next session or in the next to next.
Yes, sir, we can discuss.
In the next one. Okay. Okay
Like,
then.
if we can have an extra session, that would be better.
Sorry, extra session for.
If we can have an extra session, that would be better.
Okay. No. We will have the extra session in the next one, but I can try to accommodate the February period in the next session. Okay. Yes. See.
Okay.
Okay. Then let's see. Okay. So yeah. Thank you for joining. See you. Bye.